Are there any questions, especially from the tutorial yesterday?
I don't have questions from the tutorial, but I do have a previous question from I have a question from the previous lectures.
Okay, well, what is the question?
I was like going through the previous lectures, and I found it kind of hard to interpret the wave vector. So like, besides 2 pi by lambda, like what else?
Okay, yeah, okay, that's a good question. So the wave vector is k, and it's a vector. So it's in 3 dimension, it has 3 components: kx, ky, and kz, right? And it is its modulus k is related to the wavelength by 2 pi by lambda. Okay. And what is the wave vector? Essentially, if you have some sort of plane wave, you can represent it by, say, the real part of the imaginary part of an exponential function, or in the case of quantum mechanics, the whole exponential function, right? So you have, say, so the coefficient of the x term is essentially what you call, is defined to be the wave vector, okay?
Yeah.
So so suppose we are looking at a plane wave and we choose our coordinate reference frame such that the direction of propagation, say the direction of propagation is, say, along the x-axis, right? We can always do that if it's a plane wave, right? Because we are always free to choose our coordinate system. In that case, k dot x is going to be just kxx, okay? Because in that case, all the other components would be 0. And in that case, what we can say is that k can be, of course, positive or negative depending on the direction of propagation. We can say that the modulus of k, which is a coordinate independent object, right? We know that the modulus of a vector does not depend on what coordinate system we express the vector in. So the right-hand side, I'm expressing it in a particular coordinate system. The left-hand side is the more general definition of that. So the modulus of k is given by the modulus of kx. And because it has no other component, its wavelength is 2 pi by lambda, right? So the lambda is the wavelength of the wave vector. So once that we know what kx is in this reference frame, k is given by 2 pi by lambda, and then y and z components are 0, right? Do you follow so far?
Yeah, yes.
Okay. Now, suppose I change my coordinate system and I rotate it to some other coordinate system so that, what was x goes to some rotation matrix, 3 by 3 rotation matrix, acting on the column matrix x, right? We know we can do this. Now, since k dot x, it's a scalar, right? It's a scalar. This is not going to depend on what coordinate system we use. Then it must be that the momentum vector, the wave vector k, will transform like R inverse acting on k, so that this scalar product remains invariant. But R inverse, we know if it's a rotation matrix, is the same as the transpose of R, right? Depending on k. So you can always in your mind, if you're confused about k, you can always say, okay, k is the wave vector we associate with some plane wave, and then we can always go to a reference frame in which it is, say, going along the x direction. In that reference frame, we can relate it to the wavelength through this equation, or more appropriately, this equation, because lambda is, there's a plus minus sign here, depending on the direction, because lambda is a positive quantity. You define that to be a positive quantity. So once we have that, we can find the k vector in any other reference frame by doing a rotation and demanding that k dot x is a scalar, and therefore k changes in this way. Now let's call this k prime, this new vector, and now we can say k prime has kx prime, ky prime, kz prime components. So you can now define lambda x, lambda y, lambda z, which are the components of the wavelength, if you like, in those directions. They're defined by these equations, that k of I prime is 2 pi by lambda I. Okay? And you can just take the mod of that. Okay, Shujash?
Yes, sir.
So yeah, it's just what it is doing is that it is just a way for you to measure the wavelength. And it's mostly, so the k vector is nothing but the reciprocal wavelength times 2 pi. And it's mostly clear when you choose a particular reference frame, okay? So to summarize, let me summarize what I said. K is inverse wavelength times 2 pi. Roughly, that's the interpretation. Of course, because it's part of a vector, its component will change, blah, blah, but, the modulus of k is essentially that. Okay?
Yes, sir.
And in quantum mechanics, k is related to the momentum of the particle by the de Broglie relationship. Now, this is, one of the assumptions of quantum mechanics, or de Broglie wave mechanics. And now that's not something we can prove. We can just motivate that. Okay? If you like, it's a law of nature. Okay, any more questions, Shujash?
No, sir. Thank you.
Okay. All right, cool. Any other comments or questions? Especially, so one thing I wanted to say is that tutorial is never meant to be finished, okay, in the time given. So, so you can finish it on your own if you want, but in yesterday's tutorial, the most important problem was the first one, in my view, because it is giving you some understanding of what is the meaning of continuity when it comes to holomorphic function or differentiability. And we saw that the differentiability of a holomorphic function means that it is differentiable from any direction, whereas we saw a function which was differentiable from the x and y direction, but it was not differentiable from any other direction. Okay? Did everyone get that?
Yes, sir.
Okay, so I think enough people. Yeah, please.
On the tutorial, last tutorial, you said KdV equation. There was a KdV equation, and it was for shallow water. So what's the special thing about shallow water that we need this complex equation?
I really don't know that. I don't know how it was derived. I just know that it's supposed to represent the shallow water waves. I haven't looked into the derivation of the KdV equation. if I were to hazard a guess, I think that you'd have to take higher order derivatives if you want it to have more applicability. Okay. But
Okay.
I honestly don't know how it is derived. Yeah. This is like the KdV equation is not something I usually deal with in my work, right? I'm not a fluid dynamics person. But I thought that, let me just see, because I know that KdV equation is very famous because it admits the solitary wave. And the solitary wave, which is the archetypal soliton, and this was first recorded by an English engineer, and he basically was, I think it was, he watched a boat come to a sudden stop, and the boat created this single solitary wave which just kept on going without any attenuation of its amplitude, and he followed the wave on horseback, and until it disappeared around the bend in the river, and he couldn't follow it anymore. So I just thought that I wanted to give you an intuition about what a soliton is, and the idea about a soliton is that if you can somehow, it's not a perturbative solution. So if you have some, say, potential, some system with some potential energy like this, and suppose that this is, you have some wave. It's a continuous system, meaning it's a field theory. It's a theory where you have extended solution type waves. In such theories, you can think of the oscillations around the minima as being the usual waves, plane waves that we associate. However, so these are kind of the local solutions. However, in such theories, there are stable or metastable solutions which are interpolating, which can, say, start from here and then go up to here, or say start from here and go up to here. Someone wants to come in. Yeah. So there are all these solutions, and these are not solutions you can, you can find by doing a linear analysis. And the KdV equation is a nonlinear wave equation. So is the equation, Klein-Gordon equation, with the phi to the power 4 potential. And what I wanted to show is that I wanted to give you some intuition about how to think about these solitonic solutions. Okay.